Hello friends. In the last video, we have already learned the four formula of the projectile motions. A projectile which is thrown, making an angle theta with the horizontal plane, and it is moving under the gravitational force, only under gravitational force. And we have found the range, the horizontal distance, the total horizontal distance of projectile travels is the r, that is the range, which is given by simple ux into the time of flight. And the next formula is the time of flight itself. That is t is equal to the 2 ui by g. Okay, this is the second formula. The third formula we have found from the maximum height. That is capital H equal to uy square by 2g. And the last one is the equation of the trajectory, which is given by the y equal to ax minus bx square. And since we have found that a by b equal to the range of the projectile, then I have rearranged those terms to get ax1 minus x by r. So this is the equation of the trajectory. This equation, it is general equation of a parabola. Okay. So the equation of a parabola. So the trajectory is a parabola. Good. So here today, what I'm going to show is the projectile motion on an inclined plane using these formulas. That is when a projectile is thrown from the bottom of the, so it is thrown from the bottom of the inclined plane. And what will be the range, maximum height, time of flight? The same thing. So let us first draw the picture. So this is the inclined plane, and this is the angle of inclination is theta. So suppose this is the motion of the projectile. This is the trajectory of the projectile. It makes on the inclined plane. And this particular angle, this is u say, this velocity u, it is making an angle alpha with the horizontal line. Okay, and I am taking to match with our previous formula. I have taken the direction of the inclined plane as x-axis, and y-axis is perpendicular to that, so that I can take the component ux component. The component of the u along x-axis is ux and it is uy. Okay. So now I'm going to show draw going to drop a perpendicular from the maximum height. So that is capital H. We have to find. Okay. And this is the range we have to find. This is R. Got. So for to consider the motion, this type of motion, so the projectile is moving and it is thrown uh, uh, from the bottom of the inclined plane. We have to consider that the gravitational acceleration. the components of the gravitational acceleration along the plane is g sine theta, which is all known, and the perpendicular component to the plane is g cos theta, right? So if I compare the picture, the previous picture in this picture, so we can easily see that in the previous picture, in the negative y direction, the g is working, but now in the negative y direction, the g cos theta is working. So wherever the g's appeared in the previous formula, now they are replaced by g cos theta. This is the first striking difference. So there is a first we have to consider this. So this kind of replacement is going to be more easier to consider the projectile motions here. So wherever the g is present in the previous formula, we have to replace those by the g cos theta because along the negative y direction, so only one retardation is acting. So that is the g cos theta, the component of the g along the negative y axis. Okay. So this is a very, very important. So that is the replacement is necessary. One more striking difference is, so initially when the projectile is thrown like this, so along x-axis there is no force, fx is zero, so us is constant. But here it cannot be happened, but because when the project along this direction along x-axis, a retardation is acting, that is a g sin theta, which is acting opposite to the x-axis. So we cannot write the velocity, that is the component ux is to be constant. So ux is not equal to constant here. And that immediately shows or implies that uxt, that is the time of flight, cannot give me the range of the particle. Okay. So, so, so we have to find a way to get this range properly. So we know all the formula, and we are going to use the formula to get the range and h. So let us first write down one by one. First is the so range cannot be assigned because ux is not constant. If it is not constant, then uxt is not a range. So we cannot write the range first. So we will be starting from the time of flight. Time of flight remains same because the ui component becomes zero at the top of the trajectory, the maximum point of the trajectory. So that means the time of flight is t, can be written as 2 ui. Initially that was 2 ui by g, now it is 2 ui by g cos theta because we have already decided g is replaced by the g cos theta, right? Okay. Second, the maximum height is also 2 h, that is u y square by 2g, but now the g is replaced by 2g cos theta. So we have already found the th properly in this way. Okay. Next thing is, now our task is to find the range, and that will end our game. So find the task, instead of taking the instead of considering the component of the u along x-axis, now I'm considering the u along the horizontal axis, this axis, horizontal axis. So in this direction, the component of the u is u cos alpha, and in this direction there is no force. That means the u cos alpha is constant. So in time capital T, when the projectile reach from O to A, the the distance it will travel with this u cos alpha from O to A, O to B, right? At the same time, the particle will travel the distance OB with the u cos alpha in the same time. because u cos alpha is the component of the u along horizontal axis. So from the triangle AOB, we can easily see that OB, now we can write the OB is u cos alpha into T. But T already we know that is, so we have already found T. That's why we have already known what is OB. But from this triangle also we can see that OAB, the OA is the range, right? OA is the range. So we can write OB by, so this is the triangle I am drawing here separately to make you understand better. So this is the triangle, say. This is the right angle triangle. And this is O, this is A, and that is B. So OB we have already found u cos alpha into T. And this is the range, and that is theta. So R, it is very, very easy to see that OA, OB by OA is equal to cos theta, right? So OB, so we can find the range now. So range equal to O is the range. So range equal to OB by cos theta. So it becomes U cos alpha by cos theta into T. I just put the value of OB here. So this is our range. It is very, very easy to find in this manner. So now what we are going to write all the things explicitly. So range can be written as U cos alpha, and T is the time of flight is 2 ui by g cos theta. So in this way, that is U cos alpha, 2u cos alpha, ui, uh, and in denominator that is g cos square theta. In the last in the last line, I have to put the explicit form of the ui. So from this picture, we can easily see that if this angle, the angle of inclination is the theta and the u makes the angle alpha is the horizontal, the rest of the angle is very, very easy to see, that is it is alpha minus theta. So the ux is, so easy to see, that is ux is u cos alpha minus theta and uy is u sine alpha minus theta. I think it is easy to clear. So that is ux is u cos alpha minus theta because it is now the angle of projection. Okay, so we can write here that 2u cos alpha u sine alpha minus theta by g cos square theta. Fantastic. So now I'm going to rearranging all the terms properly. So I'm writing that is 2u square sine alpha minus theta cos alpha by g cos square theta. Okay, and good. So now I'm going to use the very important trigonometric identity, that is 2 sine x cos b. 2 is already present. This is sine A. A is alpha minus theta and B is alpha. So it becomes very, very easy to see, that it becomes sine 2 alpha minus theta minus sine theta by g cos theta. Sorry, cos theta. So that is the range. So this is the formula of range. Okay, so this is the range we have found for the projectile motion when it is thrown from the bottom of a inclined plane, okay, making an angle theta. So angle of inclination is theta, and it is and the projectile is thrown with an angle alpha, okay, which is actually made with the horizontal line. So we have found all the things. And I think the students now can understand that how is it uh, easier to deal with the projectile motion if I know the if I know the all the formula in terms of ux ui instead of u sin theta and u cos theta. It is very very easy right now. Right? Just I am just replacing the g by g cos theta and keeping the all ux and ui remaining same, and in the last I put all the things, I am bringing all the things together to get the range, the expression of the range. Is clear? I think it is clear. It should be clear because it is very very easy formula. Is it easy way to deal do it? Okay. Okay. Now we are going to see that some important characteristics that is very very important in the projectile motion. The first is that what is the maximum value of the range and how can it be found? How can it be dependent on the angle of projection? So maximum value are become R max. It is easy to see that the theta, the angle of inclination, is fixed. So only one thing can be varied, that is the all the things are depending on the value of the alpha, the angle of projection. So that means the value of the maximum of this quantity, that is sine, is 1. So sine 2 alpha minus theta is 1. So 2 alpha minus theta must be pi by 2. So 2 alpha equal to pi by 2 plus theta. So alpha equal to pi by 4 plus theta by 2. So that is the angular projection for which the range becomes maximum when it is thrown on an inclined plane. And if I put that to get the Rmax, value of the Rmax, so it becomes u square. So sine 2, I'm just writing sine 2 alpha minus theta is 1, 1 minus sine theta by g cos square theta. And in the place of cos square theta, I'm writing 1 minus sine square theta. And I'm writing 1 minus sine square theta as a square minus b square to express it again in the form of 1 minus sine theta into 1 plus sine theta. And 1 minus sine theta, 1 minus sine theta can be cancelled out. So it becomes, so R max becomes u square plus 1 plus sine theta. Here, or in the places, a g should be there in the denominator. Yes, otherwise the dimension cannot be matched from the both sides. Yeah. So yeah. So sorry, I have to make this. I have to box this equation. Very very important. So we have found the R max on the inclined plane, and we can check actually the result well because we know for the horizontal case. In the horizontal case, the value of the R was for a when the motion is made horizontal, not on inclined plane, the formula becomes ux into t, and that is ux into 2 uy by g. That means that is it becomes 2 u square sine theta cos theta by g, and that can be written as u square sine 2 theta by g. And the maximum value, our max, is we know that when the sine 2 theta becomes 1, that is u squared by g. Right? So for horizontal case, the maximum value of the R max is u squared by g. And actually we can see that this can be, we can check this result with this fact, because if I make the inclination, angle of inclination is 0, it becomes a horizontal motion. So sine 0 is 0, so it becomes so if we put theta 0 here, we can see that R max becomes the same u square by g. So this is matching. Okay. So when a projectile is thrown from inclined plane, we can easily see that how we can find the various parameters, that is various important characteristics, various important physical quantities. uh, like what we have done for the horizontal case. Just we have to remember that we have to write all the things in terms of ux and uy. Okay, then after that, at the end of the calculation, we have to put the explicit form of ux and uy in terms of the angular projection, and that we have done already. Okay. Okay. So for horizontal case, one more I have to show one more characteristic that is very very important in the sense that when a horizontal case we are considering, when a projectile is thrown, then if I uh, uh, if I will be given the velocity of the particle somehow, suppose velocity is somehow will be given like suppose 2 I cap plus 3 j cap meter per second. So initial velocity is given. So from there we can easily find what is ux, that is 2 meter per second, and what is ui, that is 3 meter per second. Right? And since we can easily find the ux and ui from this expression of u, then r, h, t, even the equation of the trajectory we can find easily. Right? All the things can be done because all the things are depending on ux and ui. So in projectile motion, in the horizontal case, for the horizontal case, in the horizontal direction, the force is zero. That is, Fx is zero, right? Hence, at every point, so in this direction, the ux is constant. That means at every point of the motion, the horizontal velocity, okay, have the same value. At suppose you are taking at any moment of this motion. So suppose here, so if the velocity at this position along horizontal direction is vx, vx must be equal to ux. So at every position, the horizontal velocity is ux because ux is constant. It does not change with the time because there is no force acting along x-axis. Why I'm telling this? Because actually this helps to solve the problems, logical problems very easily. Okay, and what we will see in the next lectures. Okay, in the next lecture we are going to solve some projectile motions problem. First, related to the horizontal case, and second, related to the equivalent case. Okay, so let me end here today. Bye.